The Silent Flight of Owls, Mechanisms, Evolution, and Biomimetic Applications in Quiet Technology. Good morning. Today I want to take you on a journey that begins in the dark forests where owls have perfected a trick that engineers would envy, flying in absolute silence. We'll trace the evolutionary story, examine the wing structures that make this possible, look at the acoustic data that quantifies it, and then explore how these ancient adaptations are now inspiring the next generation of quiet technology. Let's begin. So, why do owls fly silently? This isn't a trivial question. Evolution doesn't produce complex adaptations by accident. Two long-standing hypotheses compete to explain the selective pressure behind silent flight, and as we'll see, they're not mutually exclusive. Understanding them is the key to understanding why these wing structures exist at all. Let's look at both sides. On the left, the stealth hunting hypothesis. The logic is straightforward. A mouse has roughly 200 milliseconds to react to an approaching predator. If the owl is silent, that window shrinks dramatically. But here's a nuance from the literature. The noise must be reduced in the forward direction, toward the prey. Noise projected behind the owl is irrelevant under this hypothesis. On the right, the prey detection hypothesis. Owls hunt in total darkness, relying on sound alone. If your own wing beats are generating noise across the same frequency band as a vole rustling in the leaves, you've effectively jammed your own sonar. Kristolipian and others argue this may be the primary driver. The evidence suggests both forces likely operated in concert throughout owl evolution. Now let's turn to the structures themselves. When researchers talk about owl silent flight, they're actually referring to a triad of distinct wing modifications. Each addresses a different physical source of aerodynamic noise. And here's what's remarkable. They appear to work synergistically. It's not one magic feature, it's three. Let's examine each in turn. The first feature is the leading edge comb. If you look at an owl wing under magnification, you'll see a row of stiff, evenly spaced barbs projecting forward from the leading edge, almost like a comb or a serrated knife. What does this do? As air flows over any wing, it creates turbulence. Large turbulent eddies mean large pressure fluctuations, which means noise. The comb breaks that incoming airflow into many smaller, more organized microturbulences, dramatically reducing the acoustic energy. And critically, this effect kicks in above roughly 1600 Hz. That's not a coincidence. That's exactly where rodent hearing begins. Evolution has tuned this structure to the frequency range that matters most. The second feature operates at the back of the wing. The trailing edge carries flexible fringe-like projections, serrations that interact with the wake. Now, a conventional wing sheds large, coherent vortex structures as air leaves the trailing edge, and these vortices are loud. The serrations disrupt the span-wise coherence. They break those big, noisy vortices into a collection of smaller, quieter ones. If this sounds familiar, it's because jet engine manufacturers use exactly the same principle. Chevron nozzles on modern turbofan engines do precisely this. Nature got there first, by about 60 million years. The third feature is perhaps the most subtle, a layer of velvety down that covers the upper surface of the wing. This isn't just for warmth. It's a porous acoustic absorber sitting directly at the noise source. When turbulent pressure fluctuations hit this down layer, the energy dissipates as heat within the porous structure, rather than radiating as sound. Geyer's wind tunnel work at Brandenburg University showed something important here. The material properties matter enormously. Not just any porous surface works. Some materials tested actually amplified high-frequency noise. The owl has, through millions of years of selection, arrived at a highly specific solution. Let's look at what all this actually achieves in measurable terms. This chart reconstructs the classic flyover measurements from Kroger and colleagues in 1971, one of the earliest systematic studies. They flew a Florida barred owl with the leading edge comb intact, and then carefully removed it and repeated the measurements. What you see is striking. Below about 1.6 kilohertz, the two curves are essentially identical. The comb does nothing at low frequencies. But above that threshold, the gap opens dramatically. At 2 kilohertz and above, the comb intact condition shows 5 to 10 decibels less noise. Now, to an engineer, 10 decibels is not incremental, it's transformational. That's perceived as roughly half as loud. I want to pause on this number because it deserves emphasis. Jaworski's team at Lehigh University confirmed similar reductions across a range of owl species. And to put this in engineering context, in air acoustics, engineers fight over 2 or 3 decibels. A 3 decibel reduction is considered a significant win in fan design or aircraft noise abatement. 10 decibels, that's a different league entirely. It's the difference between a conversation and a whisper. This is why the owl has captured the attention of acoustic engineers worldwide. So we understand the biology. The question now becomes, can we translate these principles into engineered systems? The answer, it turns out, is already yes, and the results are remarkable. This is where the story shifts from evolutionary biology to applied engineering, and it's a story that's unfolding right now in fan factories, wind tunnels, and drone laboratories around the world. Let me give you a concrete example. Ziel Abeg, a German fan manufacturer, has commercialized what they call a bionic fan, directly inspired by owl wing morphology. They incorporated serrated trailing edges and a deeper airfoil profile mimicking the owl wing cross-section. The result? Up to 15 decibels quieter than their conventional fans, while simultaneously achieving up to 15% greater efficiency. That's a double win: less noise and less energy consumption. These fans are now being deployed in HVAC systems, in cooling units for wind turbines, and in data centers where noise is a serious operational concern. This is not a laboratory curiosity, it's a commercial product. Let me bring this together. We've traveled from the evolutionary forests to the engineering laboratory. The owl's silent flight is not one trick, it's a system. The leading edge comb that breaks turbulence, the trailing edge serrations that smooth the wake, and the velvety down that absorbs what remains. Evolution shaped these not for one purpose, but for two: to hunt unheard and to hear unhindered. The acoustic data confirms that these structures deliver real, measurable noise reductions. And the most exciting part? We're already translating these principles. From quieter hospital ventilation to stealthier drones, the owl's ancient solution is becoming tomorrow's technology. The question I'd like to leave you with is, what other solutions are hiding in plain sight in the millions of species that share this planet, waiting for us to look closely enough? Thank you.